Well, hello guys. Here we are, Mr. G again. We're going to do today another live for Newton's Law. Newton's Law, very important for grade 12, grade 11. I always say the same thing, but I cannot get tired enough to say it. So it is a very important. This time we're going to be dealing with Newton's second law and how to apply it when objects are connected through a string. Like you see, there we're going to solve two questions regarding two blocks that are connected to each other with a rope in between. It's a very important question for the exams of the test. It's going to be in the test, guys. It's a high probability of being in the test, either two blocks on the horizontal or two blocks moving in different direction, which next time we'll try to do one of those. This time we're going to focus on this type of question in which we have two blocks on a horizontal surface and the forces have an angle. Now, this one is practically the same as the work we've been doing or we did before, with the difference that we have now two blocks, and we are going to work separated with those two blocks as a single object. All right, because generally they don't want you to work as a system all together, and they rather want you to work simultaneous. And they say that one, they want you to work simultaneous. So let's, as usual, have a very small, tiny summary here. It is important always we start with some things we know or we knew before. So let's have a look to some important facts you must remember. And let's start with Newton's first law. So Newton's first law. Now, Newton's first law is when we apply equilibrium. And this one is just a summary, so it's going to be real fast. Here, when we, for example, have that F net is equal to 0, that is Newton's first law. If F net is equal to 0, then the object is at rest. It means it's not moving, or the velocity is constant. And guys, this one is not other thing than that equilibrium, and we've done that one before. All this is equilibrium. We spoke about equilibrium before. This one is what we call Newton's first law of motion. Now, Newton's second law says that if the net force is not equal to 0, then the object is going to accelerate in the direction of the net force. There is that part of the law must be present, otherwise you are not going to get full marks. So let's write here Newton's second law, and let's note that the formula is F net is equal to ma. Now, this time we do have an acceleration. The net force is going to cause the object to accelerate. The acceleration is going to be in the same direction as the net force, and that acceleration is directly proportional to net force for the same mass. That means that if the net force increases, the acceleration is going to increase in the same proportion. And also, the acceleration is going to be inversely proportional to the mass of the object. So the bigger the mass, the less the acceleration, but within the same proportion. So here is like a small summary of Newton's first law and Newton's second law. Also, I think we need to look at some important formulas we need to deal with when we're solving this question we are going to do right now. And the first one is going to be weight. Remember, weight is the force the earth exerts on objects that are on the surface or near the surface. And weight is equal to mg. This one is just a summary for what we are going to come. We need some of this one. From here, g is approximately 9.8 meters per second square, and is constant if we are on the surface of the earth. From here, we learn also that friction, and we have two types of friction. We have kinetic and static. The static frictional force is going from 0 to a maximum value. I'm going to write it here, maximum static frictional force. In the previous stream or live, we look at all the summary. So that's why I'm going to go a little bit faster now. This one is equal to static coefficient of friction multiplied by normal force. And if we go for the kinetic frictional force, that one is equal to the kinetic coefficient of friction multiplied by the normal force. This is regarding friction. You need to know that static friction happens when the object is not there, is not moving, but is trying to move. That is for static. The maximum static frictional force is the minimum force needed for an object to start moving. And the kinetic frictional force comes as a result of when the object is moving. Is the force from the surface on the object when the object is moving and is parallel to the surface. Finally, I want to speak about the normal, and I always say this one, and the still learners that make the mistake. Normal do not have a formula. There is not formula for normal, and therefore every time you're going to calculate normal, you have to determine the formula. This one, the only thing I'm going to point out regarding the normal is that you need to work in the y-axis. You need to work in the y-axis to be able to calculate the normal when there is a question like that, or when you need it to calculate the frictional force. So this one is a small summary. We have the Newton's first law, we have Newton's second law, we have some formulas we need, and that is just a summary. Let's start with the questions. Let's start with the questions and then see how to approach this question regardless in what directions are the object moving, within the same direction or in opposite direction. So let me move the board here. Well, I have the questions there. This question, I have it. I'm going to leave the link below if any of you is, want to get these questions. Now, let's say two blocks of 25 and 15 kilograms are connected by a light inextensible string on a horizontal surface. So you have the two blocks on the surface. A force of magnitude 240 Newton is applied on the block of 15 kilograms, forming an angle of 30 degrees with the horizontal. So I want to point out that the applied force, that 240 Newton, is only acting on the 15 kilogram block. It is not acting on the 25 kilogram. It's not touching the 25 kilogram block. So that is an important thing to have in mind. The force is only acting on the 15 kilogram block, so that applied force. All right. Now they say that the coefficient of kinetic friction is 0.2. state Newton's second law of motion inward. Guys, we stated just now, I am going to repeat it, but you have to memorize it. If a net force acts on an object, the object will accelerate in the direction of the net force. The acceleration is directly proportional to the net force, and it is inversely proportional to the mass of the object. Previous years, last year, for example, if you missed the first part, you still get 2 marks. As from this year, if you don't say everything, you do not get full marks. You will only get 1 mark. So you have to say both parts. You have to say that the net force produces an acceleration in the same direction as the net force, and the second part, acceleration, is directly proportional to the net force, and it is inversely proportional to the mass of the object. So that is question 2.1. 2.2, draw a free body diagram for the block of 15 kilograms, for the 15 kilogram block. That is the block that is at the front. And we are going to do that one real fast. So here we have the drawing. I did the drawing. The one at the front is the 15 kilogram block. This one is a 15 kilograms. Let me write it maybe here. 15 kilograms. Here, this one is a 25. It's 25. It's 25. This one is 25 kilograms. All right. So we have 15 kilograms. We have 25 kilograms. They asked to draw the free body diagram for that object there. Free body diagram. Now, when we draw the free body diagram, and this one is also changed from previous years to now, in this case, you can only represent the forces. Only forces. You cannot have components, you cannot have axes. So let's go here and look at what forces are acting on the 15 kilogram block. All right, so what forces are there? And there's a new force that we didn't speak previously. We have the applied force that have an angle with the horizontal. We have weight that is always down. I'm going to write it like this. These arrows are not accurate. We have normal up. We have friction, which is kinetic, but we also have the tension. And I want to point out about that tension. I want to point out 2 important things. First of all, that tension is for both objects. It's pointing backward for the one at the front, and it's pointing forward for the one at the back. So that is important to know. This is the same tension. It's the same tension for both objects, but for the one at the front is in the opposite direction, is backward, and in the one, or for the block at the back, is forward. That is extremely important. So this is not the free body diagram. This is just a diagram for me to look what forces are there. Now, when you do the free body diagram, 4 marks, like I say here, only forces. So we have a dot here, and this one is going to be a question at 2.2, if I'm not mistaken. What forces are acting there? The applied force. What else is applying there or acting there? There is weight pointing down. There is weight pointing down. There is normal pointing up, and there are 2 forces pointing in the opposite direction of motion. Those forces are friction, kinetic friction, as well as tension. Those are the 2 forces acting there. If you do it like this and you did not include any component or any axis, you will get 1 mark for each force represented. If you have an extra force there, you will lose marks. You cannot have extra forces, only the forces that they are represented or acting on the object. It means you cannot have any component or any axis. If you have the axis, it will be taken as a force, and you will lose marks. So that is the first part here for the question. If we follow the question, they ask you to draw the free body diagram. Question 2.3, calculate the magnitude of the acceleration of the blocks. Now, to calculate the magnitude of the acceleration of both blocks, I'm going to use my other board, which I'm going to clean real fast. We have to work simultaneously. So we have to work in both blocks at the same time. Now, for this question, we are going to redraw the free body diagram, but this time I am going to include the axis because it will make my work easier. So I'm going to write here for 15 kg, and I'm going to work here for the 15 kg. On this side here, I'm going to work for the 25, for 25 kg. So I'm going to work simultaneous here with both blocks. For the 15 kg, we already have the free body diagram, there it is, but we are going to redraw it, and this time we are going to include all the axes. And it's quickly. It's not nothing that is going to take you the whole day to do. It's very quickly. It must be straight. It is there. And then here is the y-axis. Now this one will help me to find out the components, etc., etc. So today, my mistake here. This is x, and this is y here. Now, what forces are acting? I'm redrawing the same free body diagram, just with the axis. So this one is no 4 marks. All right. So we have here the applied force. Remember, we learned previously that if you have a force that is in between axes, we have to determine the component. We have to break it into components. We also have here the weight. We have here the friction. And we have here the tension. So back, you have 2 forces, and we have to point that one out and be careful don't you mess up. And then we have the normal as well. So those are the forces that we have. It is the same free body diagram as before, but this time I have the axis because I want to break that force into components. And that is what I'm going to do. I'm going to take it down here, and I will have here right on the x, I will have FA in x. If we look at the angle, they're giving us this angle here, which is equal to, and let's go into look quickly, 30 degrees. This one is 30 degrees. So if you look here, this one is adjacent side to the angle, so it's going to be equal to applied force multiplied by cosine of 30 degrees. Do not memorize this one as well, because it can change sometimes. All right, so if we break this one into the y component, we have here, you break it here to the y-axis. There we go. This one is F A in y. You can see it's opposite. It is the same as if we draw it there. And it's going to be the applied force multiplied by sine of 30 degrees. So that is when we break forces into components. Now, we are looking for the acceleration. So we have to work in the x-axis. Why on the x-axis? Because the object is moving on the x-axis. So I am going to apply Newton's second law on the x-axis. Let me write here in x so you know where I'm working. In x-axis. There we go. And I'm going to mark here. I'm going to work in the x-axis. The x-axis is this axis here. I want to show you what forces are there. There you go. We have 3 forces in x. We have the applied force in x. That is the one that is right on the axis. We have the applied forces in x. We have friction backward, and we have tension backward. If we take the direction of motion as positive, then the applied force is positive, tension is negative, as well as frictional force. So Newton's second law for this block will be F net is equal to ma. That is Newton's second law, and you get a mark for just writing that one. We're working in x. So what forces do I have in x? I have the applied force in x, not just applied force in x. I have tension, which is negative. I have kinetic friction, which is negative, and all that is equal to ma. There we go. That is what we have here for this specific object. Now, we do not have none of those. We do not have the applied force in x. We do not have the friction. We do not have tension. We do not have A. We have many unknowns there. Some of them can be calculated. We have the formula for kinetic frictional force. We can calculate that one for the 15 kilogram block. So we need to calculate the frictional force, and we need to calculate the component of the force in X, the horizontal component of the force. All right, so let's try to do that one. And let's do it step by step. I'll have to take this space for this calculation and then use the other little board for the other calculation. So let's begin with the applied force in X, that is equal to applied force multiplied by cos of 30 degrees. Now, if we substitute, we have that the applied force is how much? It's 200 and something, 40. So this one is 240. Let me write it down. Me and my short-term memory. 240 cos of 30 degrees. This one is equal to, let me calculate it. I have calculated, but I want to do it again. Multiplied by cos of 30 degrees. We get in 207.84. This one is 207.85 Newton. That is the horizontal component. We have that one now. Okay, we don't have friction. So let's calculate friction and let's use this space. I'm going to raise that for 25 kilogram block and I'll do it in the other little board. So let's calculate here friction, kinetic friction. Now, kinetic friction is kinetic coefficient which is given to us multiplied by the normal. A problem, we don't have the normal, so it's a good practice. In a previous slide, we explained how to calculate normal when there is a force that makes an angle. There is no formula. We started speaking about that. So to calculate the normal, if we go to the free body diagram here, the normal is on the y-axis. So to calculate normal, we must go to the y-axis. All right, the object is not moving in the y-axis, so it is in equilibrium. If the object is at equilibrium in the y-axis, everything that is on top is equal to everything that is at the bottom. What do I have on top on the y-axis? I have normal and I have the applied force in y. That is in the y-axis on top. What is at the bottom? W. All right, so in this case, normal plus applied force in y is equal to W. There we go. That is why you cannot memorize this one because it changes. So now if you rearrange, you get the normal is equal to weight minus the applied force in the y-axis that we can also calculate because we have the angle. So we have to calculate that one. Let's do it real fast. We have to calculate this one. Applied force in y. It's a lot of calculation, but not necessarily difficult. This one is applied force multiplied by sine of 30 degrees. We already did write it on top. There it is written. So if we go here, the applied force in y is equal to 240 sine of 30 degrees. This one is equal to 240 sine of 30. I get that is 120. So this one is 120 Newton, right? That is 120 Newton. So we have now, we can substitute here and calculate normal. Remember, W is mg. So normal, in actual fact, is going to be equal to, W, which is mg minus 120. If we substitute, the mass is 15, 9,8 minus 120. So normal is going to be equal to, these boards are very small for all this calculation because it's a lot of calculations in this question. So we have, let's do that one quickly. It's 15 times 9,8. You can check the calculation, guys. Minus 120. I get that it's 27 Newton. So the normal is 27 Newton. That is the normal. Now we can come back here and calculate the friction. There is the calculation of the friction on top. There's the calculation of the friction. So I'm going to use the other board. I did not want to, but I have no option. So let's calculate it there. Then I have to write all this one. So friction here is equal to kinetic coefficient of friction, which is given to us, and is going to be 0,2 0,2 multiplied by the normal, which we did calculate. It is here, and it's 27 Newton. So multiply by 27, that is the kinetic frictional force. So this one is going to be equal to, if we write it here, this one is 0,2 times 27, I get that is 5,4. So the frictional force is 5,4 Newton. There we go. So we have friction now. Now that we have friction, we may come down here and substitute in this equation. We have the applied force, we have the frictional force, we do not have tension, we do not have acceleration. So yes, you may have, or you are going to have, two unknowns. So let's substitute. Let me take all these pens away from them. So let's write it here on this side, because the space is very small on my white little board, so we can do all those calculations. So I'm going to rewrite here the equation real fast. Here on top, let me rewrite it. It is FA in X minus T minus FK is equal to MA. I'm rewriting. I just rewriting everything. So FA in X is 207,85 minus T minus friction, which is 5,4, is equal to MA. There we go. That is the equation. I'm going to show you the equation now. That is the equation. There we go. We have M. We don't have A, but we have M. So we can substitute here 15. Now, we have common factors. We have this number and this number. So we can solve that one. It is 207,85 minus 5,4. We get that is 202,45 minus T is equal to 15A. Guys, we cannot go on because we have two unknown in here. We have two unknown. We don't have acceleration. We do not have tension. So we have to stop there. We are going to call this one equation 1, and we're going to stop there. So we're going to work now with the other object. The other object is a 25 kilogram block. I'm going to do it on this corner. There will be a less calculations, and I hope is enough space in that. So now for the other block, what do we have? Let's do here, right here, for 25 kg. We still have to calculate the normal for this one, but normal for this one is better. Something for that. Just let me pick up that thing that for there. Just a second. One second. I keep my light. There we go. I'm sorry, I kicked my light there. Okay, so now we are here. We have to work for the 25 kilograms, okay? For the 25 kilograms, the forces are the following. There's only tension to the right. Remember, we spoke about tension. For the block at the front, it's backward. For the block at the back, it's forward. This is T. And we don't know T. We are looking for T. We have W down. We have weight up. Sorry, normal up. And we have the frictional force. Those are the forces acting for the 25 kilogram block. All right. Remember, we're working for the acceleration. So we are going to still work in the x-axis. So here in x, what forces we have? What forces we have in x-axis for this specific block? We have tension and we have friction. Only those. This is easy. Remember, applied force is not acting on the 25 block, but is rather acting on the 15. You can see it there, in the question. Okay. Now here, Newton's second law once more. F net is equal to MA. This one is for the 15 kilogram block, for the 25. All right, for the one at the back. So here we go. In X, what we have? Tension positive is pointing to the direction of motion. Frictional force is backward. So we have that it's going to be tension minus kinetic friction is equal to m8. Guys, we don't have friction. We have to calculate friction for this block. All right, but we know how to calculate it. Friction, remember? Friction, kinetic, is equal to kinetic coefficient multiplied by normal. This is the new normal. It's for the new object. Here, in the y-axis, you only have normal and weight. Only those two. So for this question, the normal is equal to the weight. And I hope you are listening carefully. For this question, only for this question specific, normal here is equal to weight. Why only in this question? Because there are the only two forces in the y-axis, and the object is at equilibrium in the y-axis. So if we go here, then we can calculate now the kinetic friction, which we are going to do so real fast. We have that kinetic friction is equal to 0,2, that is the kinetic coefficient, multiplied by normal, which is equal to W, which is equal to mg. So this one is equal to 25 multiplied by 9,8. That will give you the kinetic frictional force for the 25 kilogram block. Let me calculate it quickly here. 0,2 times 25 times 9,8. I get 49. I hope my calculations are right. I often make mistakes with calculation. I don't pay too much attention to those. All right, so that is the friction. Then we can substitute in here. We are going to do that, and we're going to do it right below the other equation, because why not? Because why not? So we're going to have that this T minus kinetic friction that is calculated, is here at the bottom, is 49. So it's T minus 49 equal to 25A. Guys, here we cannot go on because we have two unknown. We are going to call this one equation 2. And then all we have to do is to work simultaneous with these two equations. If you note here, the tensions are the same, so they cancel each other. Otherwise, learners like to substitute. So you can substitute for T if you think it's easier. Then you can come from equation 2 and you say T is equal to 25A plus 49. And then you substitute in there. All right, that is what we're going to do. I generally like to add the two equations instead, but we can do this one here. We can do this one here. So let's substitute that tension in there. Let's substitute the tension in there. Looking at, yeah, there we go. So the tension in there, we have 202,45 minus T, but T is going to be 25A plus 49. So that is what I'm going to substitute. Minus, in bracket, 25A plus 49, and all that is equal to 15A. There we go. So now you open bracket here. So it's 202,45 minus 25A minus 4A is equal to 49, no 4A, 49, my handwriting, 15A. And then you just rearrange this one accordingly. So this A is going to the other side. We have that this 202,45 minus 49. Let me clean that 9. 49, I'm thinking of something, I'm writing something else. Minus 49 is equal to 15A plus 25A. Guys, the rest is now calculation. So from here, we may calculate A. Let's do calculate A. I don't want to do all the steps because there will be too many. So let me do this and write 202,45. Guys, you can do the calculation with me and see if I get the correct answer, which might not be. 15 plus 25. Okay, after my calculations, I get that this one is 3,834 acceleration. So the acceleration is equal to 3,83 meters per second square. That is my acceleration after you solve this one. But the question did not ask for acceleration. The question asked for It asks for acceleration and then for tension. So now you have to calculate the tension. The acceleration, this is the way how to calculate acceleration. You have to work simultaneous. And now to calculate tension, we just have to take this acceleration and substitute here by the T. So T, and we're going to do that one real fast, T is equal to 25A, which is 3,83 plus 49. That will be T, which if we calculate, let me just do that one real fast. This one is 25 times 3,83 equal, and now I add 49, and that gives me 144,75. 144,75. That is T. This question is done and dusted. Guys, you can ask if you have any question. It's a lot of calculation, but it's not necessarily difficult. It's the same. It's the same work as before, with the difference that you have to work simultaneously. You work for both blocks at the same time. So that is the first question, which is this one here. Question with an example from a material I developed for revision. There we go. So if there is no questions, I can move to the next question, which is similar but not the same, because the angle or the force is a little bit shown different. Instead of being pulling with a force, this has been pushing with a force, and it's different. It's a different mostly for the normal. I always want to work with the normal because learners make a lot of mistakes with the normal. So let's go to the next question. This question it is in this specific way. Most of the question the same as the previous one, but not everything. The question say a learner tried a push toy using two blocks with masses of 1,5 and 3 kilograms there. The learner then applied the force of 25 Newton acting down at 30 degrees to the horizontal to the 1,5 kilograms. So note, it is being pushed, it is not pulling. Now, since the moment you push, the normal force is going to increase because you're pressing against the floor a little bit. All right. Acting downward at 30 degrees to the horizontal to the 1,5 kilogram block by means of a light ring cord. That is an important information. Causing the toy to move across a flat rough horizontal surface as shown in the diagram below. The coefficient of kinetic friction between the surface and each block is 0,15. They gave us the coefficient of kinetic friction. Guys, the first part of the question is to calculate, is to state the law, Newton's second law. We already spoke about that one 2 times. I am going to repeat it. Make sure you write it every time you do a question. If they ask you for the same law, write it. It's nothing wrong to write the same law many times. Many times, the more you write, the more you memorize, okay? So the coefficient of kinetic friction is this one, okay? State the law. If a net force acts on an object, the object is going to accelerate in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass of the object. 2 marks for saying like that. Write it down, even if it's 5 times in 5 questions, okay? The next question says calculate the magnitude of the kinetic frictional force. Let me take my face there. Frictional force acting on the 3 kilogram block. Calculate the kinetic frictional force of the 3 kilogram block. If we're going to work for the 3 kilogram block, first, let's do the free body diagram. They don't ask us to draw it. So this drawing, which is going to be question 4.2, this drawing is going to be with axes, it's going to be with components, if any, because what I want to know is how things work in that. All right, so I am drawing here what is going on so you can see real fast, okay? Let's see if we can do now the question. They ask us to calculate frictional force. For this one, we are going to be doing the free body diagram, but this free body diagram is going to include the axis. This is not for marks, it's for me to understand what is happening in here. All right, so it is for this one. They ask me to calculate the friction for that one. Look here, calculate the magnitude of the frictional force for the 3 kilogram block, that is the block at the back. All right. Now, for that block, what is or what are the forces acting? First, tension to the front. This is tension to the front. All right. This force, which is the applied force, is only for this block. It's not for the block at the back. What other forces we have here? We have friction, which is actually what they're asking us to calculate. We have normal, and we have weight. Let me erase this, and then we have weight down. Those are the forces. Okay, so I'm going to do the free body diagram because we're going to need it later for the other part of the question. So for the 3 kilogram block, I'm going to write for 3 kg. The dot is there, the axis. This one is not for marks. This one is for me to study and do the question. X, Y, forces are T to the right, FK to the left, normal up, weight down. There we go. So in this question, they ask us to calculate the kinetic frictional force. Quite easy. Let's do the kinetic frictional force. What is the formula for kinetic frictional force? It's equal to kinetic coefficient of friction multiplied by normal force. We do not have normal force. Now, I always repeat the same thing. There is no formula for normal force. We have to determine. Guys, even if it's easy, try to determine because then you memorize and you practice. All right, so normal force is in the y-axis. Is in the y-axis. So if we go here, in the y-axis, we have weight and we have the normal force. And the object is at equilibrium in the y-axis, is not moving. So top is equal to bottom. It means that normal is equal to weight, which is equal to mg. There we go. But this is not a formula for normal. This is just working through to get the normal force. Okay, so normal is equal to mg. If we substitute, this one is the 3 kilogram block, it's 3 times 9,8. The normal force is equal to, let me do the calculation here, 3 times 9,8, 29,4 Newton. Now we may substitute in there. Okay, so if we substitute in there, is the calculation a little bit down. So now we substitute, we have that Fk is equal to kinetic coefficient of friction. Let me see, my memory is not good. It's 0.15. So this one is 0.15 multiplied by 29,4. There we go. Trying to squeeze because of the space of my little board. So Fk is equal to, if you multiply this one times 0.15, guys, I get 4.41. 4.41 Newton. This one is for the 3 kilogram block, for the block that is at the back. I hope it's clear. I hope you understand that calculation. That calculation is not that bad. Okay? But if it's any question, you can always ask. Right. So the next question, we're moving on. The next question here say, I have to take off my face. Draw the free body diagram, show all the forces acting on the 1.5 kilogram block. The 1.5 kilogram block is at the front. Now that one is the one I want to point out because the force is now being pushed, is not pulled. Now the forces cannot go towards the dot when we drawing the free body diagram, but rather going away from the dot. Right. So what I mean is the following. This one is question 4.3. We're going to do it right here. 4.3 here. Now the force that is in the picture is like this. All right. There is the force. It is like that. But when we draw in free body diagrams, we cannot draw forces towards the dot, but rather away from the dot. So instead of doing that, we have our dot as it is, our dot as it is here, and then the force is, remember, it was in this direction towards, we're drawing it away from the dot. That one is the applied force. All right. Here, what other forces are acting? There is normal force, which in this case is going to be greater. That if you pull it up, we have weight down, and we have frictional force to the left. And what other force is acting? Tension for the first block is also pointing backward. Okay, so the same tension here is pointing in the opposite direction there. So here we also have tension going back. Those are the forces acting on that block, guys. Remember, in this free body diagram, I cannot draw axes. I cannot break into components. Otherwise, you are not going to get full marks. Here, you will get 1 mark per force if it's exactly like this one. You cannot get, if you draw axes or you break into components the force, then you will lose marks. All right? So this is the free body diagram for marks for this specific block that is at the front here. Now, if we do it now for us to work, then I break it into components. So it is the same one. It is the same one, but this time I'm going to break it into components. I'm going to break it into components. This one is X, this one is Y. I like to break it when I'm solving the question because I can see the X and the Y axis. I want to see what is in there. So look here, same force is going to be there. This angle is the one that they gave us, and that angle is going to be 30 degrees. This angle here, that is 30 degrees. I'm going to just do this. This one is the applied force. The rest is the normal force. We have friction, kinetic, we have tension to the back. Note those two forces there. We have weight down, and we have normal up. All right, those are the forces. Now, this is in none of the axes. I make sure I break it into, my daughter is a little bit difficult. Now I make sure I break this force into components. All right, so I'm taking it to the X. This one is applied force in X. And if I break it into the Y, I have applied force in the Y axis pointing down. And that is extremely important. It's pointing down. Look here. All right, it's pointing down there. So this is now the free body diagram I need when calculating. Now, we need to calculate friction eventually. The question asks us to, and let me just go here quickly to see what is the next question. Where is it? It's there. I have to take off my face. Draw the free body diagram. We cannot see the last part of the bottom question. 4.4, calculate the magnitude of the kinetic friction, and then calculate the magnitude of the tension. So let's calculate the magnitude of the kinetic friction for that block of 1.5 kilograms. Yeah, there. Frictional force. Now, to calculate friction, remember we need normal. Where is the normal? The normal is on the y-axis. We're working on the y-axis to calculate normal. Look here. Look at that. Up is equal to bottom. What we have on top, we have normal force. What we have at the bottom, we have two forces here. We have the applied force in Y, we have W. So in this case, we have the normal is equal to applied force in Y plus weight. That is how we calculate the normal force. This one is equal to applied force in Y. It's opposite to the sign. This one is the Y1. So this one is applied force sine theta plus mg. This one is how we calculate normal for this specific question in which the force is being pushed instead of pulling. All right? The rest is calculation. So we can do this calculation real fast. Normal is equal to applied force. Let me go there. It's 25 Newton. So this one is 25 multiplied by sine of 30 degrees. Pardon? Plus 25 multiplied by 9,8. That will be the normal force. So if we substitute, we have 25 sine of 30 plus 25 multiplied by 9,8, I get 257,5. I get that the normal in this question, let me see where can I write it because I'm running out of space. The normal here, normal there, is equal to 257,5. So normal, Newton, that is the normal. So from here, we can calculate now the frictional force. We have the normal, we can now calculate the frictional force. Let me place this other board here. Frictional force for that specific object is equal to kinetic coefficient multiplied by normal. This one is 0,15 multiplied by normal, which is 257,5. The kinetic frictional force for the first block, in this case, if we go here, we get that is 0,15 times 257,5. Making sure I don't make mistake with the numbers, is 38,625. That is the calculation of kinetic frictional force. 3,38, yeah, I'm writing wrong numbers here. 38,625 Newton. That is the kinetic frictional force for the first block. Kinetic frictional force for the first block there. The last question, they ask us to calculate the tension for those two blocks. Let me show you the picture. They ask us to calculate the tension. To calculate the tension, we have to calculate the friction. And I show you in the previous question. It's exactly the same. We have to work simultaneous. The free body diagrams are done here, so I'm not going to redo it. We just have to work in the x-axis, for each of the blocks. All right, so let's begin with the 3 kilogram block, which is easier because it's at the back. Let me show you. It's at the back. 3 kilogram block is at the back. So we can start with that one. So I'm going to write here for 3 kg. Right, in x. I'm going to work in x because the acceleration is in x. So what we have here, F net is equal to ma. What forces are acting there for the x-axis? We have tension, let me show you. We have tension to the right, we have kinetic friction to the left, and we did calculate the kinetic friction already. So if we go here, we have that this tension minus kinetic friction is equal to ma. We substitute the values. We have all the values except for T. T is unknown. Kinetic friction we calculated and it's 4,41 and this is equal to 3a. Guys, we cannot go on because we have two unknown. This one is therefore going to be equation 1. We stop there. We cannot go on. So we're going to work now for 1,5 kg in x. That one is the one we were just working here, this one here, in x. In x, we have the applied force in x, kinetic friction, and tension. Those are the 3 forces in x. So here we have that net force is equal to ma. We do it like that. In x, we have the applied force in x minus tension minus kinetic friction, which we did calculate already, and that is equal to ma. The applied force in x is cos, is adjacent to the angle, so this one is applied force cos of 30 degrees minus t minus kinetic friction is equal to ma. We have all the values except for tension and acceleration. We're going to have two unknown. So here, the applied force, I forgot, 25 is 25 multiplied by cos of 30 degrees minus t minus the kinetic friction is 38,625 equal to 1,58 because the value of the mass is 1,5. This one is just calculation. We have to calculate. Let me just calculate what I can here. 25 cos of 30 minus 38,625. We get, okay, is a number that is not well calculated somewhere because we get a negative answer. I have to move back. I make a mistake, some calculation here. Let me see what the calculation is. Sine 30 plus, oh, there is 2,5, it's 1,5 and I multiply by 25. Okay, the mistake is here. I make a mistake with the calculation. With my daughter crying next to me. Here, when calculating the normal, the mass I substitute 25 and the mass is 1,5. So let's fix that one quickly here. And then this one is 1,5. 1,5. This is happening with live. It's not a recorded video. So these things happen here. So let's recalculate that one quickly. It is 25. 25. Was it 25? Was it 25? Yeah, 25 is the fourth. So it's 25. I'm sorry about that one. Let's fix it. 25 sine of 30. That is why you should be interacting here. Plus, and then I get that is 1,5 is the mass. Let's check. 1,5. I wrote 25 here, guys. 1,5 multiplied by 9,8. And that we get 27. So the normal force, look here, we got 257. It's actually 27. It's actually 27. Let's fix here. We have to fix a couple of things then. Not too many. 27,2. 27,2. Therefore, we have to fix the friction, which is here. It's here. This one is 27,2. There we go. And then if we multiply 27,2 times 0,15 is equal to 4,08. All this one here is 4,08 Newton. We coming back here. This one here, there we go, is 4,08. There we go. So fixed and sorted. If I have somebody crying next to me, it's difficult to focus. And this is live. So live, when you do a live video, this is what happens. Mistakes happen. So now we do the calculation. Is 25 cos of 30 degrees minus 4,08. We get that is 17. We get that is 17. This one here. 17,57 minus t is equal to 1,58. We cannot go on. This is going to be equation 2. All right. Now we have equation 1. We have equation 2. Different options to do it. You can do substitution. You can add the equation. I personally like to add the equation by my learners. The majority like to substitute. So let's substitute. Let's substitute the first equation here, which is easier. Let's rearrange this one. If we do that, we get that t is equal to 3a plus 4,41, and then we substitute this one in equation 2. All right. I hope you are following me there. So what do we have here? If we do the substitution, we have that is 17,57 minus t, but t is going to be this number here, is 3a bracket plus 4,41, and that is equal to 1,58. Here, you open bracket, 17,57 minus 3a minus 4,41 is equal to 1,58. Guys, the rest is just calculation. The 3a is going to the other side there. So let's rearrange here. Let me see. It's 17,57 minus 4,41. We get that the 13,16 is equal to 4,58. A is equal to 13,16 divided by 4,5. We get that is 2,92. Acceleration is 2,92. 92. Guys, you may check the calculation in case I have made a mistake with the calculation, which it might happen here. It's live videos are like this. And then from here, we substitute A in the formula of tension, which I'm going to show you here. And that is how we calculate the tension, which is actually the question here. So T is equal to 3A plus 4, 1. T is equal to 3 multiplied by 2,92 plus 4, 1. Let's do that one. 3 times 2,92 plus 4, 1. We get that is 12,86 Newton. Guys, this is the end of the question. Now we are officially done with this question on the live. It's been difficult. My daughter was crying the clothes too, and I was very distracted there, so we made mistake with calculation. Guys, any question? Now it's open for questions. I hope it helped. These questions could be tricky, and it is going to be in the test. I'm still thinking what live I'm going to make next Saturday, if it's going to be for the grade 12, maybe organic chemistry, or I'll do another Newton's law, but now blocks that have or are moving in different directions. Something like, maybe I can show you quickly. I'm thinking to do in the next live, maybe if I'm doing Newton's law, I'm thinking to do those blocks that are hanging like this. Something like this. I'm thinking, but you can always suggest, you can ask, you can write comments, like the videos, write comments, and then you can suggest, say, this one is much needed, and I'll do it. I'm thinking on chemistry as well. The grade 12 is currently doing organic chemistry, and it might be difficult. Some other learners ask me about ticket timer. I might do the experiment maybe better, because the old one had some background music that is disturbing. But guys, it's open for questions. I don't know if there's any question. This stream lasts 1 hour and 3 minutes so far. I don't know if there's any question. I'm ready to answer. If there is no questions, then we'll see. But yeah, that is the stream, guys. So I hope it helped. This topic is difficult. This topic can create problems. That's it. So if there is no question, guys, I just said I'm going to leave the link in the description. I'm going to leave the link where you can find this material, and you can find more materials. It is going to be in my link tree. Thank you, Molemo. I'm happy to help. I hope it helped you. I hope it helped you. We already done it at school, so I don't know. But thank you for being here, boy. I much appreciate it. And it's my pleasure. It's my pleasure to help you. Guys, if there's no question, much love to you all. Enjoy the rest of the weekend. Good luck, and see you next time.